Can we go faster than light? If I practice enough, I feel like I could swing this sword faster than the speed of light. Don't believe me? Let me explain. When I spin the sword, the whole blade rotates at the same angle. Because every part turns through the same angle, the tip travels a much greater distance than the part near my hand. So the tip moves faster. The farther from the center, the faster it goes. So if I get a long enough sword, the tip could exceed the speed of light. You don't believe me? Good. You're right not to. This is probably the first example that comes to mind when people ask, how can we break the speed of light? And no, swinging a sword won't do it. I'll explain why, but in one of the three methods I'm about to share, I'll actually show you a real way to use the sword, or something like it, to exceed the speed of light. And none of these violate Einstein's special theory of relativity. Tachyons. But wait, didn't Einstein say nothing can travel faster than light? Have you ever actually seen him say that? Because Einstein never said exactly that. This is one of the most famous and most misunderstood topics in all of physics. So let's clear up the misunderstanding first. Once we do, the three methods will start to make a lot more sense. The first method involves tachyons. The name comes from the Greek word for swift. These are hypothetical particles that are thought to always travel faster than light. We've never observed them. In fact, many physicists think the idea is complete nonsense. But before you dismiss it, some very serious physicists, including Nobel Prize winners, have been strong defenders of tachyons. They argue that just because we haven't seen them doesn't mean we shouldn't be looking. Here's why. Einstein's special theory of relativity says, more precisely, that you would need infinite energy to accelerate an object to the speed of light. Imagine a rocket in space with unlimited fuel. It keeps accelerating, but as it approaches the speed of light, it takes more and more energy to push it just a little bit faster. You can keep burning fuel forever, but you'll never quite reach light speed. It's a bit like flooring a car. At first you accelerate quickly, but at some point, no matter how much you push the pedal, you just can't go faster. Now, Einstein arrived at this conclusion starting from a very strange assumption. He proposed that all inertial observers, no matter how fast they're moving, will measure the speed of light as the same constant value. No matter what speed you're traveling at, if you measure the speed of light, you always get the same answer. That sounds almost insane. Think about it normally. If a rocket is moving at 300 kilometers per hour and you're stationary, you see it moving at 300 kilometers per hour. But if you're also moving in the same direction at 100 kilometers per hour, you see the rocket moving at only 200 kilometers per hour. That's how everything works. Einstein said light is different. If you're stationary, you measure light at 300,000 kilometers per second. Now imagine you're moving at half the speed of light, 150,000 kilometers per second, in the same direction as the light. You'd think you measure light moving at only 150,000 kilometers per second relative to you. But no. You still measure it at 300,000 kilometers per second. If you turn on your headlights while traveling near light speed, it behaves exactly like turning on headlights while parked. Light always moves away from you at light speed, no matter what. That's why you can never catch up to it. Einstein started with this bizarre assumption and built a theory that turned out to be correct. That's why we now treat the speed of light not just as a speed limit, but as a fundamental property of the universe. So how could tachyons possibly exist? Let me give you the perspective of one of the great minds of physics, someone you've probably never heard of, George Sudarshan. He made foundational contributions to quantum optics, and here's what he said about tachyons. Suppose a geographer says that nobody can live north of the Himalayas because nobody can climb over those mountains. That would be an absurd conclusion. People in Central Asia were born there. They didn't have to cross from India. In the same way, faster than light particles, he was pointing to something many physicists overlook. Einstein's theory says you can't accelerate a particle to light speed, but it doesn't forbid a particle from simply being born faster than light. Light itself is an example. It's created at light speed and disappears at light speed. It doesn't accelerate to that speed. The Himalayas represent the speed of light. Below, all the slower than light particles we know. Above, perhaps tachyons. That's why Sudarshan said, if tachyons exist, they must be found. And if they don't exist, we must be able to clearly state why. Sudarshan's name may not be widely known, but his foundational work was recognized by the Nobel Prize Committee, twice awarded to other scientists building on his ideas. He died in 2018 at 86 without ever receiving the Nobel himself. Many physicists were outraged and wrote letters to the committee, but it never happened. Cherenkov radiation, the second way to exceed the speed of light, is real, not hypothetical at all. You can literally see it with your own eyes. Before Einstein's 1905 discovery, three scientists, Heaviside, Descoudre, and Sommerfeld, made a bold claim. If a charged particle like an electron moves through a medium faster than light moves through that same medium, strange things will happen. But after Einstein's theory arrived, their work was forgotten. After all, nothing can go faster than light, right? Then in 1934, a young Soviet physicist named Pavel Cherenkov noticed something strange. He was studying a radioactive sample submerged in water and observed a very faint blue glow. So faint, in fact, that to study it, he had to go into a completely darkened room, cover himself with a blanket, and wait a full hour for his eyes to adjust to the dark. Then he'd lift the blanket, make his observation, cover back up, and have his assistants take notes. They didn't fully understand what they were seeing, but a few years later, two other Soviet physicists, Ilya Frank and Igor Tamm, traced the glow back to those three forgotten scientists and figured out what was happening. Here's the key. When we say the speed of light, we usually mean the speed of light in a vacuum, but light slows down when it enters a medium. In water, for example, light slows by about 25%. Einstein's cosmic speed limit applies to the speed of light in a vacuum. So other particles can actually travel faster than light moves through water, without violating relativity at all, because they're not exceeding the vacuum speed limit. When a charged particle does this, something analogous to a sonic boom happens. A supersonic jet compresses sound waves in front of it into a cone. That's the Mach cone. The same thing happens here, but with electromagnetic waves instead of sound waves. The waves pile up into a cone, and that's the blue glow Cherenkov observed. We now call it Cherenkov radiation. Cherenkov, Frank, and Tamm received the Nobel Prize for this discovery, and today you can see this characteristic blue glow in nuclear reactors. And interestingly, it's also how we detect neutrinos, those elusive ghost particles, deep under Antarctic ice, a full kilometer below the surface. Apparent superluminal phenomena. Now for the third method, and this is where I bring the sword back, not to swing it this time. A different trick, and this time, when I say speed of light, I mean the speed of light in a vacuum. And there is no limit here. This can go as fast as it wants. It's not hypothetical either. These are real, observable phenomena. I want to be precise about that word. Phenomena, not objects, not particles. To understand what I mean, let's first go back to why the sword can't really exceed light speed. When I apply force to spin the sword, that force propagates as a wave along the blade. Since it's a rigid material, we can't see it. It looks like the whole sword moves as one piece. But if it were a flexible material, like a guitar string, you'd see it. Or think of a whip. When you crack it, you can see the wave travel to the tip. That's a mechanical wave. The atoms of the material push on each other, creating a kind of atomic Mexican wave. But because it's a mechanical wave, it travels at the speed of sound, which is enormously slower than light. Sound in air travels at about 343 meters per second. Light in a vacuum travels at about 300 million meters per second. So forget about swinging a sword faster than light. Even if you could, the tip could only approach light speed, never reach it, and near light speed the tip would start lagging behind the handle, and the blade would warp or shatter. Now let's think about scissors. Imagine the point where the two blades cross as they close. Could that crossing point travel faster than light? Well, scissors are basically two swords, so the same limitation applies, but there's a trick version of this. Imagine a paper guillotine, the kind used in print shops. The blade has a slight angle to it. The narrower the angle, the faster the cutting point travels from one side of the paper to the other. In theory, you can make that angle so small the blade is nearly flat. And if you press it straight down, both ends of the paper are cut at the exact same moment, effectively infinite speed. Make it just slightly angled and the cut travels faster than light. But notice, nothing is actually moving from one side to the other. No matter is being accelerated. The cutting point isn't a physical thing, it's just a geometric location we're defining. There's no object to push, so no force is needed, and Einstein's limit doesn't apply. The same is true for a laser pointer. Not the laser itself, but the dot it makes on the wall. Sweep your laser pointer across a wall, and that dot moves. The farther the wall, the faster the dot travels. Here's why. You start at one angle, open the laser, and after 1 second, the beam is swept to the other end. The dot has to cover whatever distance is on the wall in that 1 second. Put the wall far enough away and the dot moves faster than light. But the dot isn't a physical object. You're seeing independent photons hitting different parts of the wall at slightly different times. If your eye could do a long exposure, like a slow camera shutter, you wouldn't see a dot, you'd see a line. It's a purely perceptual event. There's no object being accelerated, no force being applied, no violation of special relativity. Your shadow works the same way, by the way. Under the right conditions, your shadow can move faster than light. Now, don't let the word perceptual make you think these phenomena are trivial or unimportant. Astronomers realized how significant this was even before Einstein, back in the early 1900s, when they observed a nebula that appeared to be expanding faster than light. After Einstein's theory came along, those observations were brushed aside. That's impossible. But the observations were correct. It took nearly 70 years for astronomers to take it seriously again and work out the explanation. What they found is this. If something is expanding at close to, but still under, the speed of light, and it's moving at just the right angle relative to us, it can appear to be expanding faster than light. This is called superluminal motion, and it's well documented today. A striking example is V838 Monoxrotis. Astronomers watching the structure expand over time calculated that it seemed to be growing faster than light, but there's no actual matter moving that fast. What was happening is that the star was surrounded by a cloud of dust that was mostly invisible. The star suddenly flared up, like a flash, and that flash lit up the surrounding dust. As the light from the flash propagated outward, it illuminated different parts of the dust cloud at different times. When astronomers measured how fast that lit up region was growing, it appeared superluminal, but nothing was actually moving faster than light. It was just light revealing something that was already there. So let's bring it all together. 3 ways to exceed the speed of light: tachyons, Cherenkov radiation, and apparent superluminal phenomena. The last 2 are real, observable, and well understood. Cherenkov radiation lights up nuclear reactors and helps us find neutrinos at the bottom of the world. Apparent superluminal motion shows up in nebulae and stellar explosions across the galaxy. Tachyons remain hypothetical. We haven't found them. Maybe they don't exist. But what's remarkable is that all 3 of these, in different ways, were ignored or dismissed for decades because of a single sentence. Nothing can go faster than light. That sentence was never quite right. And by taking it too literally, we may have slowed ourselves down. Today's story was ultimately about something bigger than physics. It was about the courage to look beyond visible limits, to question what seems impossible, to keep asking even when the prevailing wisdom says the answer is already settled. Sometimes the greatest breakthroughs in understanding come not from discovering something new, but from finally paying attention to something that was always there.